Okay, we are here and talking about tomographic projections. And we're going to continue to talk about tomographic projections today, and then we're going to get, I think, into some fun stuff if we have time. But before we do it, we want to walk through the homework. So let me go ahead and share my screen, and we will. Okay, everybody sees my picture with my wife. Isn't that a cool picture? That was taken in a hotel in Seattle. And I tell people I have many wives. So let's go ahead and start with this. I think that we have covered 37 sufficiently. Can everybody see my screen? Okay, the Oblate and Prolate Spheroid. I think that we've talked about it enough. For the Oblate, one needs to just have one dimension larger than the other two, which are the same. For the Oblate, one dimension is smaller than the other two, and that's the Oblate spheroid. So that's what it is. Okay, let's do the which of the following operations commute. Let's take 3 at a time. So I'll ask somebody to do the first 3 and somebody else to do the next 3. Is that okay? And let's see, we'll have, unfortunately, Chris is constrained to be on a phone right now, so he won't be able to participate. 1, 2, 3, 4, 5, and Glauco isn't here. So we have 5 because Glauco forgot his headphones. So David, you're 1, Aiden, you're number 2, Adam, you're 3, and Justin, you are 4. Oh my gosh, I only need to flip 2 coins. Today I'm using a very nice American dime, okay, and a penny. Nice penny. So there's no variation. Okay, so we have 1, David, 38. I'm going to give you permission. I'm going to stop sharing my screen. I'm going to give you permission to participate. I shouldn't make fun of my own vocabulary, should I? Okay, you can participate now. Okay, David, can we hear?
Yeah, sorry.
Okay.
It took me a moment to realize that I was muted.
Yeah, it took me longer. Go ahead.
Okay, so starting with a horizontal oval, and I rotate it first and then shift, get this. I shift it and then rotate, and I get this. So therefore, clearly rotate and shift do not commute.
That's fine. That's a good engineering proof, isn't it?
Yeah.
Okay, so that's fine. Go ahead for scale and shift. That's fine.
Okay. Yeah, so start with a square centered at the origin. Scale first and then shift, or shift and then scale. Shift then scale ends up much farther from, about twice as far from the origin. So scale and shift do not commute.
Okay, so in both cases, you've disproved the proposition by giving a simple counterexample.
Yeah.
Okay, scale and rotate.
Yeah, so start with an off-center ellipse. Scale, make it bigger, and then rotate like 45 degrees counterclockwise, or rotate and then scale. Looks like they do the same thing, and I reasoned that this is the case because scaling affects only the magnitude of a vector from the origin to a point, and rotating affects only the direction of that vector. So and direction and magnitude are can be changed in any order.
Okay, go ahead and unshare your screen.
Okay.
Let me ask, does anybody disagree with David on number 3?
I got that it does
I
not
do.
commute.
Okay, Justin, could you show your result? Wow, you did it. You did it a lot more.
Yeah,
You did a math thing, didn't you?
I did a math thing.
Okay, that's great.
Yeah, so I
And
did
plus,
it by.
plus you need to spring and get thicker paper so it doesn't bleed through from the other side. I'm just pulling your leg. Okay.
I was like, where's the? I think those are just erase marks.
Oh, those are erase marks. Okay. It
Yeah.
looks like you did it in pen, but okay, maybe
I
not.
think
Go
it's
ahead.
just the
Go
way I
ahead.
scanned it. Yeah. Okay. Yeah.
I'll
So
shut up.
I ended up doing mine out of order. So this first one's actually C, and I drew out the rotation matrix and the scaling matrix and applied them in one direction and then the other direction. And as you can see, is if you apply scaling first, you scale T1 and T2 individually by M1 and M2. But if you apply like scaling second, then M1 is being scaled by the whole equation rather than just each part.
That looks to be perfectly right. Excellent. Thank you. Go ahead and unshare your screen. So I don't believe they do commute. Does anybody have a geometrical example that they could share? David gave a geometric sample, but he chose something that looked like they do commute. So this is, of course, a problem with engineering proofs. Did anybody draw a picture of it?
I did the math proof too, but I guess they would be commutative if you were scaling by the same factor in both directions.
Yes, that has to be the case. Yes. Mm-hmm. You have to scale by the same factor in both directions. If you don't, when you scale, you only stretch out the rubber band of the T1 axis, where if you rotate first, you're stretching it out both in the T1 and the T2 axis. And I think that the ellipse, the circle, can be a little bit deceptive there, right? So no, they don't commute. Thank you, guys. Okay, let's do the next 3. Let's see, we have Aiden, Justin, and Adam. Adam, you're not showing me your shiny face.
Oh, didn't realize.
Much better. Doesn't that make everybody's day a little bit better by seeing Adam there? I think it does. Okay, Aiden 2, Justin 3, and Adam 4. Or 0. 0. So you're up again. So we're looking at transpose and scale, scale and shift, and transpose and rotate.
Okay. There we go. My pen was dying, so it got a little faint here, but I think we can still read it a bit. So I did the math proofs as well.
So where did you get your new pen for E?
My drawer.
See, okay, big effort. Okay, go ahead.
So part D was scale and transpose. So this one you transpose first, this one you scale first. You end up with minus T1 over M1 and minus T2 over M2 for both of them. So I say that D does commute. And then,
okay, before we go, let me ask you this. We didn't specify, we were kind of sloppy on transpose. And I think this was my fault for not stating the problem properly. But transpose in 2 dimensions mean you flip on one axis and then you flip on the other axis. You can also talk about transposition in 1 dimension, say just on the T1 axis.
Yes, I think this would hold in that case as well.
Do you? Okay.
Because just looking at it, it's the only place the sign change comes from. And you're either dividing T1 by M1, minus T1 by M1, or you're multiplying T1 over M1 by minus 1.
No, you're exactly
So
right. And it comes from the fact that both of the matrices are diagonal.
Yes.
Okay.
Yeah, I guess the other thing we assumed here was that we were in 2 dimensions.
What? That's fine.
Yeah.
Okay, go ahead with E.
Yeah.
So they do.
My Googling did show that it's different in 3 dimensions, but I stuck with 2.
It's different in 3 dimensions, really?
For some of them it is. I can't remember which one, but I saw that one of the operations was commutative in higher dimensions, but not in 2.
Interesting. Okay, I've never thought that abstractly. That's an interesting question. Okay, go ahead.
So this next one appears to be transpose and shift.
Transpose and shift. Thank you.
So this first one we transposed then shifted. This one we shifted then transposed. You end up with minus T1 minus tau 1 minus T2 minus tau 2 versus minus T1 plus tau 1 minus T2 plus tau 2 does not commute.
Okay.
Because you are distributing the minus signs from the transpose or not. Then the last one, we rotate and transpose, or transpose and rotate. So first one, you get the minus cosine, minus sine, plus sine, minus cosine. Then it works out again on the other one that is still minus cosine, minus sine, plus sine, minus cosine. And I believe this one would also work with different definitions of transpose.
Okay. Well, certainly for the one that you chose, it does work, doesn't it?
Yes.
Okay, wonderful. Wonderful. Okay, did anybody go ahead and unshare if you would, Adam. Did anybody do a geometrical thing? Show a figure? I like figures. I like to visualize stuff. The math is good.
Yeah,
Okay, David, go ahead and show us what you got for those. Or Aiden, did you do that? Did you do the geometrical part?
No, I
Okay,
didn't.
go ahead, David, then.
all right. Let's see.
Oh, and Glauco joined us. Hi, Glauco. You forgot your headphones, huh?
Yes.
Oh man. Okay. Always carry a separate set of earbuds. Is my philosophy. Okay, go ahead.
All right. So yeah, I got that transpose and scale commute.
Oh, you just did it. You just did it. Oh, okay. Yes. You transposed in 1 dimension there.
And shift. Yeah.
Okay.
And I got that transpose and rotate do not commute.
Okay, now Adam, you got that they do commute?
Yes.
Okay, let's see if we can tear apart one of the conclusions here.
I think David is right because they commute when you have the case Adam analyzed that if you use -1 to the nth power for each of the diagonal elements, they change positions.
Okay, so therefore what you're saying is that David and Adam are both correct because David did the transposition in 1 dimension, Adam did it in 2.
Right.
All
Okay.
right.
Well, we see that we see that things aren't so so obvious. And again, this is my fault for not specifying exactly my definition of transposition in this problem. Okay, and then finally for F, transpose and rotate.
Okay. Yeah, so that was the last one. Transpose and rotate.
Do not commute.
We just finished.
Okay.
So they.
Okay, well, good. Thank you, David. Appreciate it. Go ahead and unshare your screen. Okay. Have you noticed, guys, we've got this down. This idea of sharing screens and stuff. This works out very well. Okay, let's see. We have 3 people left. We have Glauco, Justin, and Aiden. So, okay, I have to reassign numbers. Aiden, you're number 1. Who am I forgetting? Oh, Justin, you're number 2, and Glauco, you're number 3. Okay. Nod. Okay, good. Okay, we have number 1, who is Aiden. So let me ask you this. Can you tell me the Hankel transform, not by sharing your screen, just what is it for FR is equal to 1? What did you get?
I got a impulse.
At the origin? Okay, I think,
sorry.
okay. Yes, it is an impulse. And
So it would be delta rho.
delta of rho. Now this is something that is kind of weird because I'm not sure what delta of rho means. Let me share you my problem here and see if you can help me with it, okay? In 2 dimensions, okay, my special board is not working, so you'll have to bear with me just a second because I don't know what's wrong. So much for seamlessly sharing everything. Okay, it goes up here. I'm following wires around because I'm not smart enough to put together wireless connections. It goes around a little post. Goes around a little post to keep it on my desk so that if the dog comes in, he doesn't jump up and down and drag all of my equipment off my desk. Then it goes around and where does it, oh, does it go there? Okay, let me try to plug this in again and see if it works. Try this, and if this doesn't work, okay, uh-oh. I'm in a heap of trouble, guys. Let me try one more thing. I'm gonna unplug it from my hub and try to plug it directly into my old computer. Okay, something went boom, boom-da-doomp. So how about that? Silly thing. Okay, here's my problem, and help me out here. Del of rho is equal to del of the square root of T1 squared plus T2 squared. Now, the proper answer to this, I know, is del of T1. The right answer is del of T1 times del of T2. This is the right answer. So the Hankel transform, if I can use the Hankel transform of just 1, is equal to a couple of deltas. Why do I know that? Because this is exactly the same as the Fourier transform, a 2-dimensional Fourier transform of 1, right? The Hankel transform and the 2-dimensional Fourier transform are exactly the same. So I know this is the same, or I know that this is the correct answer. The question, and I don't know the answer off the top of my head as to whether this is equal to this, because that's what the delta of rho is equal to. Does that make sense?
Yeah, I would think that this is, well, like delta is commonly, like we compare it to a rectangle function and becomes a delta at the limit as the width approaches 0. And the delta of rho is delta of a circle, whereas delta times delta is the is a rectangle, like in 2 dimensions. So, but as at the limit, as they both approach 0 size on the T1, T2 plane, they become equivalent.
Yeah, so I think what David is saying is that, and I'm going to have to think about this more. I'm not really sure about it. By the way, now my mouse isn't working. Ah, okay, frustrating. That that if we take this cylinder here and we have it have a unit volume, that if we place this, have this diameter go to 0 and the height go to infinity at the same time to keep the volume equal to 1, we might get exactly the same thing. So I'm not sure about this. So this is an interesting result. Okay, go ahead. Go ahead to the second one. Justin. Or no, Aiden. Aiden was up.
So, do you want me to share now? Because you didn't ask me to share.
Yes, please go ahead and share.
Okay. So this was the Gaussian. So we talked about doing it as a separable function instead of using angle transform. So what I did was I did that. I separated them, then got the transform, which we know is the same thing. And then I combined the exponentials together and got this, and that becomes the rho squared that we talked about in class.
Okay.
So I ended up being the Hangel transform indirectly, kind of. So that's what I did for that. Now for C, I'm still kind of confused about when I can just take rules in the first dimension and apply them to higher dimensions. But I literally just took the scaling theorem or scaling property, not theorem, scaling property, and applied it to this problem. And I don't know if that's technically correct or not.
No, you have to go back to basics, and I don't believe that's correct. Did anybody else get a different answer?
I got an m squared, x of mp.
It's an m squared. I don't see the picture. Who's talking?
It's Justin.
Okay. Justin, would you go ahead and share your screen and show how you got the m squared? Ah, okay. That's an interesting way of doing it. Go ahead and explain what you're doing there.
You need to unmute.
Yeah, I never realized I was muted. Okay, so can you hear me now?
Yes.
Okay, so yeah, so I use the two-dimensional Fourier transform where you're using substitution to solve this integral and to bring it into like something similar that we can use for like saying, oh, this is the Fourier transform. And so using substitution, I just use some dummy variable and plug that in, and you get 2 factors of m from the derivative. So when you substitute for like sigma or omega equals t1 over m, and when you take the derivative of that, you get a factor of m in your substitution. So whenever you do that, you're left with an m squared of the Fourier transform of u1m, u2m.
Okay, that's perfect. Go ahead and unshare your screen. No, that is that's perfect. Here's another way to do it. And my mouse started working for some inexplicable reason. Here's another explanation. We know that f of rho, here's just the definition of a Hankel transform, right? That's the definition of the Hankel transform, correct? So we're asking ourselves, what is the corresponding case? What is the corresponding case when instead of just R, you have f of R over M? Whoops. Right? That's what we're trying to figure out, correct? So what we're going to do is we're going to use a dummy variable. And what's the best way to do the dummy variable? Let me make all of these R hats, if you will. So not to confuse us, we're going to set R is equal to R over M, R hat over M. So that dr hat is equal to mdr. Everything's very nice right now. And we're left with this is equal to the following. What is R hat? R hat is equal to Rm, or let's see, is that right? R is equal to R hat over M. So R hat is equal to MR, right? And then we get an F of R, and then J naught 2 pi. And we get an R over M times dr hat, which is equal to mdr.
Would it not be 2 pi r rho m? 2 pi r m rho?
Oh, you're right. You're right. Thank you. Let me go ahead and erase some of this. R hat is equal to MR. Thank you. And then we have dr hat is equal to mdr. Now, what was shown was that there were two m's that came out of here, at least when we did the substitution of the two-dimensional Fourier transform. There's also two m's that come out of here, one for the m, the first m for the r, the other one for the differential. So this is equal to 2 pi, and we're going to suck out the m squared. And then we're going to lump the m with the rho. So what we get is m squared, and what is left is exactly the Hankel transform of f of r, except that instead of rho, it's at m rho. So there's two m's which come out of here. So it is an m squared. One of the ways to think about it, which comes out of the math, if you scale, for example, a circle to be a larger circle. So you take a magnitude of 1, and then it goes to, you take a circle with radius 1, magnify it to be with a radius of 2. To do so, you're magnifying in 2 dimensions, aren't you? You're magnifying in T1, and you're magnifying in T2, right? So you're stretching it this way. That brings out 1 m. You're stretching it this way. That brings out another m. So that's the reason we get the m squared, kind of in a geometrical way of looking at things. Is that okay?
Yes. I arrived to the same result by applying the rotation, scale, and transposition property of the multidimensional Fourier transform, where you divide by the determinant.
Okay.
So the
we have a,
determinant.
yes. Okay.
Yeah.
That's right. Okay.
The determinant comes to be m squared. So.
Right. My goodness, we haven't got to that as of yet. Unfortunately, I skipped that. We have to go back and do that. Yeah, no, that's true. Yeah, what Glauco is saying is one of the theorems that we skipped was the scale and transpose theorem, where if xt has a Fourier transform of x of u, what does x of a matrix times t Fourier transform to? And if Fourier transforms to, and we haven't proven this, and I should have, it Fourier transforms to A inverse transpose of u divided by the determinant of A. Let's see, is it the determinant of A inverse? I think it's a determinant of A inverse. Is that right, Glauco? Check me on that.
No, it's just the determinant of
determinant of A, okay. Yep. Yeah, no, that's right, determinant of A. So this is, compared to one dimension, x of t mt in one dimension, Fourier transforms to the Fourier transform of u over m divided by m, right? That's the scaling transform. So above, we have a generalization of this idea, don't we? Because we can't divide by a matrix, right? If we have x of at, we can't say x of u over a matrix. We can't divide by a matrix. But instead, we can do an inverse of the matrix, and that inverse turns out to be transposed. As we've talked about in here before, the inverse of the transpose is the same as the transpose of the inverse. And so it doesn't matter how we do this. But so this is the generalization of the scale, rotate, and transpose. We kind of covered individually the scale, and we covered the rotate. We covered the transpose, but we didn't cover the general case. This is the general case. So this A matrix, it can be an inversion. It can be a rotation matrix. It can be a scaling matrix. It can be a transpose matrix. It doesn't matter what this A is. This is one theorem that fits them all. If we multiply by A in the other domain, we multiply the frequency variable by the inverse transpose. And what Glauco is saying is that he used this in order to demonstrate this, because what is A? At least in the two-dimensional Fourier transform, it's 1 over m times 1 over m. This is something very similar that we've just seen before. So the determinant of it, so if this is A, what's the inverse transpose? That's the inverse transpose, right? And so it says that if we stretch these things out by m1 in both directions, then in 2 dimensions, we crush it in by a value of m in the other dimension. Just exactly like we would expect with the scaling theorem. And what's the determinant of A? It's equal to 1 over m squared, right? If we're scaling a circularly symmetric function. So 1 over the determinant of A is equal to m squared. And so that's where Glauco got this result that we saw here, okay? So that's a third way, numbers of ways to work this problem. And yes, the intuition and going back to previous theorems doesn't work here. It doesn't work here because the other theorems don't apply unless you interpret them correctly. Okay, let's see. I'm sorry, who was doing this? Aiden, you were doing this, is that right?
Yeah.
Okay, did you get, oh wait, you got this one, but I bet you didn't get the squared term, right?
For C?
No, for D.
Yeah, I don't think I did D right. I was really hoping not have to do 3, but of course that didn't happen. But I mean,
okay.
but
Okay.
I would this is the one I was struggling with.
Okay.
And of course I have to explain it, and I can't. So
Well, let's.
I didn't do it right. I don't think. But
Okay, Justin. Anybody else want to do D?
I got something for, I got a jink minus a jink, but I'm just realizing now that I accidentally wrote it as a sink. But
No,
I
it is the difference between two jinks. Okay, who volunteered? Okay, David volunteered. Okay, David, go ahead and show what you have. David always volunteers. I just noticed I'm having a bad eyebrow day. Did you ever have a bad hair day? I have a bad eyebrow day. Okay, David, go ahead.
All right. So I defined the annulus function by 2 circle functions, and I took the transform of each and then took the difference. So
okay, you did it, and this is totally correct. But what's a J1 row over row?
Okay, so yeah, all right, so that is a jink.
Yeah, so it's the difference between two jinks. Plus, I think that there's a beta squared and an alpha squared there for the same reason that we had it before.
Okay.
Go ahead and unshare your screen. Did
Okay.
anybody else get that with the difference between two jinks?
I think I do.
Okay, Adam, would you go ahead, please?
So yeah, I did the same thing, define the 2 rectangle circles, one of radius beta minus one of radius alpha, that those will transform into 2 jink. And then we know from part C, we have the m squared f m rho theorem. So it's beta squared 2 jink beta rho minus alpha squared 2 jink alpha rho.
Yep, that's it. That's exactly right. Now, David, the answer that you got was totally correct, but you killed a fly with a sledgehammer. You could have just said, oh, the Fourier transform of a circle is a jink, instead of redefining it as a J1x over x. So what you got was totally correct, but I think it was, in my mind, the difficult thing to do it. It was the difficult way to do it. It was not the in Paul Erdos's word in the Book of God. It was not the simplest way to do it. Okay, let's boogie on here. Derive the inverse Hankel transform. Who did this and is really proud that they did it in a very simple way? Wow, nobody is volunteering. So therefore, the only one that's left, I think, is Glauco. So Glauco, did you get this one?
I do the same process as the Hankel transform derivation, just changing the variables. I follow the same steps.
No, that's exactly right. Do you have anything written down you can show us?
Yes, I can share
Thank you.
my screen. Is here is big enough? I can amplify it.
Glauco, you are a multimedia guy. You write in ink and in pencil. That's cool. Okay, go ahead.
Okay, so the inverse Hankel transform. I get the definition of the inverse.
Tell you what, Glauco, what you have here is totally correct. Let me just explain it to
Okay,
everybody.
thank you.
We start out with the inverse Hankel transform. Then we do exactly the same substitution that we did last time, making the rectangular things into polar form. And then we go down and we recognize a trig substitution there in the middle of the page. And we do the same thing. We recognize that the nested integral third equation from the bottom is a J1, as he has from the second equation from the bottom. And it turns out that you get exactly the same thing for the inverse Hankel transform as you did for the forward Hankel transform as given by the last equation. The math is exactly the same, Now, of course, with the inverse Fourier transform, you use e to the plus j, and for the forward transform, use e to the minus j, but that washes out here. All of that washes out in terms of the derivation. So yeah. In fact, if you got here and you said, oh my gosh, if you just stopped after the second step and you said, you know, I'm going through the same steps as I did for the forward Hankel transform, and I'm going to get exactly the same thing as I did for the forward Hankel transform, except things would be reversed, then that would have been okay. So a circle in the T1, T2 domain has a Hankel transform of 2 Jank. A circle in a unit circle in the frequency domain has a inverse Hankel transform of 2 Jank. The Fourier dual theorem is so simple you don't even have to keep tracks of the plus and minuses. It's very, very simple there. Okay, Glauco, thank you. That's perfect. Okay, now we're going to get a little bit more fun. Did anybody have any fun with this at all? Okay, what is the circular two-dimensional transform of a circle of radius alpha shifted to be centered at T1 at this point in the T1, T2 plane? And usually when I say a circle, I think we all know that that's a circle that's 1 inside and 0 outside. So let's go ahead and start with that one. See who got that one. Here's my random number generator. Oh my gosh, I have the world's skinniest coin. Do you know in Japan what the coin is there, the yen? Did you know a 1 yen coin will float? And it's like this thing. This is a little aluminum slab here, just a little aluminum penny, and this would float if I put it in water. Not because it's lighter than water, but the surface tension keeps it on the top. So if you floated the thing and then you put just a little bit of soap in there, it would shrink. It would shrink. It would sink, but without the soap. So the yen, at least when I was in Japan, number of years ago, the 1 yen coin floats. I think it's the only coin that floats in international currency. So that's going to be one of our flippers here. Is this? I don't know if it's a 1 yen thing. It is. It's a 1 yen thing. No, it isn't. You know what it is? It's one of these tokens you buy for playing arcade games. So, well. That's not going to be worth me using because I'm going to have a hard time telling whether it's heads or tails. I couldn't even read what was on it. So, okay, we'll start out. Aiden, you're 0. Justin is 1. Adam, you're 2. Glauco is 3. David is 4. Anybody I'm missing? No, because Chris is not with us. Number 1. So that would be Justin.
All right, I believe you have to. Yeah, there you go. Okay, so 41. The way I did it was I took the Hinkle transform of a circle at the origin and then expressed it in U1, U2 units, and then shifted it after. So you have
That's
f
it.
of r. F of r is equal to the rectangle function of r over 2 alpha, and that becomes 2 alpha squared g of rho, and then you shift it and get the following answer that's boxed.
Okay, great. No, that's perfect. Yeah, this is the thing in all of these problems is you can mix the Hankel transform with the two-dimensional Fourier transform. Go ahead and unshare your screen if you will. Thank you. Perfect, perfect, perfect. Okay, the same as A, but the function inside is 0 inside the circle and 1 outside. Justin, did you get this one?
Yes, I did.
Okay, go ahead and do that one. We'll make it a double here. This one is very simple once you know what to do, right?
So you talked about us in class and gave us a hint that it's just kind of like you have a slab that's all 1 and you just cut out the center, which is where the circle is, which is 0. So you can treat that as 1 minus your circle and then do your Fourier transform of that. And based on what we got in A, we can use the same formula, but the 1 transforms into a delta U1, delta U2 minus the same thing we got in part A.
Yeah, I'm not sure what that is. The 1 minus pi t over 2p t2 over 2q. I don't know what that is. I don't think that's right. Your answer's right. Your answer's right, but I don't know where the math on the line above came from.
Yeah, now that I'm looking at it, I don't know where I was going.
Okay. Well, the answer is right. You just take the answer in the first part and you subtract it off from a delta function.
I may have started going down a wrong path and then realized I went wrong, but then I have to erase it.
Okay, good. Understood. Okay, go ahead and unshare your screen. Okay, let's look at the next one. Justin, I'm going to let you do this one too. Okay, you're on a roll. We're going to let you do a trifecta here. Okay, the same as A, but the function is -1 inside the circle and 1/2 outside. And then we'll start with somebody else for the next one.
Okay, so this one I didn't really do a whole lot more like calculations with it. I just noticed that the magnitudes representing from B changed in C. So for the delta functions in B, I just called that as like each delta function had a 1/2, so that would go to a 1/4, and then your sign, which was just subtraction, now becomes a positive because the area inside the circle is -1 instead of 1.
Yeah, that looks right. That totally looks right. Did anybody get a different result? Yeah, I'm almost certain it's just weighting the inside the circle and outside the circle and getting the corresponding result in the other domain. Okay, thank you, Justin. You did great in the trifecta, and you know the odds of doing that are very high. If you bet on that, they give good payoff. Yeah. So I don't know what the odds of the trifecta are. Okay, 2 circles of unit radius. One is centered at 1 minus 1, the other one at -1, 1. And the function is 1 inside the circle and 0 outside. Okay. Let's see, we have 4, which I don't, do we have a 4? Who's 4? 0, 1, 2, 3, 4. David, you're 4.
No, you started with 0. So there's,
Oh, 0. 1,
Yeah.
2, 3, 4. We have 5 here. I think David is still 4. What number were you, David?
Actually, I think I was 4. Sorry.
Okay.
Yeah. I'm sorry. I didn't get past 41C.
Okay. So let's reflip, and you will be recycled because we're very environmentally friendly in this class. Uh-oh. I dropped one of my random number generators. Okay, I got 1 again. No 1s. Justin's gone already. And now I get 4 again. How many do we have left now, by the way? 1, 2, 3.
0, 2, 3.
We have 3 left. Okay, let's see. 1 again. Justin, you should have gone to Vegas now. 0.
Okay, that's me.
Okay, great. Go ahead and restate the problem because right now I forgot it. It's the end of a long day.
Yeah, I really need to start writing the problem statement, I think, because I don't have it written down. Let me, I'm sorry, let me, because I have my problem here. So
Well, no, no, that's fine. You have it exactly right. Yeah, I don't think you need to do anything. Your first equation there is one circle minus another circle.
Yes. Wait, so on D, well, it looks like, I don't remember. I'm sorry, I have to pull it up. There's no way I'm going to be able to do this if I don't have it.
Okay, yeah, I don't think your notation is righteous, though.
So I'm doing D, right?
Yes.
Okay. Two circles of unit radius. One is centered at, okay, yeah. Okay, yeah, so what I did here is first I started with, just the circle with the radius, excluding the shift, kind of like with the others.
Yep.
But then I wanted to actually write it in the time domain.
See, you can't do it that way. That has to be, if you go from your first equation to your second equation, rho is the square root of T1 squared plus T2 squared.
Yeah.
Right.
Okay.
What you have there is a 2-dimensional rectangle function.
Yeah, I see that now.
Okay, so yeah, this isn't going to work. I think your answer is right, but
yeah,
it kind of.
I'm still pretty sure my answer is right, but I understand what you're saying about this being wrong.
Okay. Did anybody else go ahead and unshare your screen? Yeah, I think you were thinking the right thing, but didn't get the beauty of the math down correctly. Anybody else get this?
I believe I think I got it.
Okay, Justin,
Yes.
go for it.
So what would be getting 4 in a row be called?
That'll be a quadfecta, right?
Quadfecta.
Or a quafecta? I don't know what they call that. Never heard of a quafecta.
Okay, so yeah, so I drew out the circles here, and they're both of unit radius of 1, centered at 1 and -1 and -1 and 1. And I just took the since it's 0 outside and 1 inside, you just add up each circle, and using the same formula that we got in part A, just applying it at the correct radius and shift. That's what I got. So
that's
P and Q
right.
equals,
No, that's right, but you didn't finish the problem. You have an e to the minus j, and then the other place you have an e to the plus j. Do you see that? In your second equation, the first equation is e to the minus u2 minus u1. Do you see that?
e to the minus.
Right there, yes, where your cursor's at.
Yeah, e to the minus j 2 pi u2 minus u1.
The next one is e to the plus j2 pi u2 minus u1.
Oh, you're saying it should be plus?
No, no, I'm saying if you reverse the order of the variables in the parentheses, that minus turns into a plus.
Does it? Because your P and Q are different because it's the different circle now.
Yeah. Okay. Here. Thank you. No, you got the right answer, but you just didn't complete it. Thank you. Go ahead and
Okay.
unshare the screen. Anybody else get it to the final point?
I think instead of changing the sign of the J, he changed the order of the U1.
Yeah, no, that's fine, but it's
Okay.
still the question I'm getting to is it the final solution? Is it the solution that you want? Here's the idea, and Justin is totally correct here.
Would you call that a tetrafecta?
We'll see what he does next time. Let's see. Was it in this quadrant and this quadrant? Is that right?
Yes.
Okay. So we know that one of these circles transforms to a two jink row, right? I don't know what I just wrote out. I have no idea what that is. I feel like a medical doctor writing a prescription here. Which is equal to 2 jink square root of u1 squared plus u2 squared. So that's perfect. Now, this one gives me a 2 jink square root of u1 squared plus u2 squared times an e to the what? It's a plus j 2 pi u1 plus u2. Do I have that? Or u1 minus u2. Is that right? Do I have that right? Is that the same as yours, Justin? You had the right answer at this point.
I believe I had minus j in front of that, but you were saying that should be plus j at the e to the minus j 2 pi.
Did you, but you had a u2 minus u1 here. I'm having a u1 minus u2.
Oh yes, I see. Yeah.
So I think
That's
it's the same thing.
Yeah, same thing.
And then the other one gives the jink. Hell nuts. The other one gives e to the minus j 2 pi u1 minus u2. Do we agree with that? I think that probably jives with what you had too. Is that right, Justin?
Yeah, I think so.
Okay, and so this becomes 2 times the jink. And here's the beautiful finish. And you should always think of this when you see two different things that are symmetrically opposed to each other. Notice both of these have the same beginning, right? This one has an end of e to the plus j. This one has an end of e to the minus j. What's e to the plus j plus e to the minus j? It's a cosine.
Cosine.
So you got it up to this point, but didn't recognize the simplification that could occur here, which is very interesting. So anytime you see a function in T1, T2, and you see something up here and you see something down here, there's a cosine. Because what is this equal to? Isn't that equal to this? Convolved with a couple of deltas, one up here and one down here, right? If you convolve something with a two-dimensional Dirac delta, you get the thing centered where it is. So up here and down here is equal to the function centered convolved with a couple of Dirac delta sheets. And these are going to inverse transform. So the inverse transform is, if we convolve in this domain, we multiply in the other domain. So we get here a jink times a e to the plus j, e to the minus j, which is a cosine.
So basically, whenever there's something that's rotationally symmetric around the, rotationally symmetric around the origin, you can expect a cosine.
Expect a cosine, right? E to the plus j, e to the minus j.
I guess 180 degrees rotationally symmetric. Might be different if it's 120 degrees.
Both of the translations have to be the same at the origin. That's the takeaway. Ever how you want to rotate it is fine. I don't think you can rotate it. They both have to be. They both have to be. They both have to be the same. For example, I'm saying that this. Okay, let me do something profound here. This would have to be countered here by this. In other words, this and this are exactly the same. They're exactly the same because if you translate them to the origin, in both cases, you get this, right? So you can't flip one. You can't flip one. You can't rotate it. It has to be exactly the same at the origin. I'll give you one more. What if you had something like this? If you had something like this, it would be e to the j, whatever this is. So it's e to the j, whatever the shift is in T1. And then you would have a cosine of U2 because the shift in this direction matches the shift in this direction. I'm sorry, the shift in this direction matches the shift in this direction. And this would give you a cosine as a function of U2 in this case. So hopefully that simplifies things a little bit. Any questions on that? Okay, and then here's kind of a simple one. Anyone want to grab this one? A circle of unit radius inside a square with a linear dimension of 2. Both are centered at the origin. The function is equal to 1 outside the circle and inside the square.
I can do it.
Okay, Adam, go for it.
There we go. Finally, let me unmute. All right. So like the annulus problem, we're doing the outside minus the inside, where the outer part is a square on this one as opposed to having two circles. So the square, we take the two square functions, one on T1, one on T2. We divide by 2 to scale them so that they have a length of 1. So then that becomes 2 sinc 2u1 times 2 sinc 2u2. Then for the circle, it's the unit circle, so it's just the square function of r over 2 turns into 2 jink of rho, which we can write as u's instead. So then we just combine the sinks and subtract the jink and get that answer.
Okay, now that's perfect. Why don't you do the last one also, because that looks like it's right.
All right, so yep, so we know that the Hinkle transform of f of r is capital F of rho, and then since we just wanted to do the derivative with respect to T1, we can apply the one-dimensional derivative property. So we just do j 2 pi u1 times f of rho, which can be written as u.
Yes, and the problem is dt, the derivative with respect to t1 of this circularly symmetric function.
Mhm.
What operation would that be? If you had an image, go ahead and unshare your screen, if you would. If you had an image, it doesn't even have to be circularly symmetric, and you did a derivative with respect to t1. In other words, going the derivative with respect to t1, what would you expect if you had an image?
That'd be edge detection.
You would get edge detections because you would get the derivative every time the gray level changed from a 0 to 1. You get a big derivative, wouldn't you? At least as it changed going this way. It wouldn't catch the up and down, but yeah, it would be a derivative. So you would get the the vertical edges of the image by doing that. Which is kind of cool. Okay, let's see what else. What other damage can we do here? Very good, Adam. That was very good. Okay, number 42. Did anybody get this far? Okay, Adam did. Justin? Okay, why don't we shoot it back to Justin then? What is this in terms of the Hankel transform? Now notice this is exactly the same as the Hankel transform, except the Bessel function isn't there, right? The Bessel function is gone. Okay, Justin, go ahead.
Mute, yeah. Okay, so yeah, so it's just the Hankel function evaluated at f of, instead of f of rho, it's f of 0. We have to figure out what j of 0 of 0 is, and I've over here on the right expressed the j of 0 of 0 and found it to be j of 0 of 0 is 1, so therefore that expression is just equal to f of 0, which is the area of the signal.
That is so cool that you figured out what J0 of 0 is. I'd probably looked it up on Google or something. But you're right. I did give you the equation that you could compute the Bessel function at the origin. It is 1. And if you go back in the slides and look at the picture of the Bessel function, J naught, you'll see it's equal to 1 at the origin. So, yep. That's exactly what it's equal to. Now, is f of 0 same as the two-dimensional Fourier transform evaluated at 0? Anybody?
It's the same as when u1 and u2 are both 0.
Yeah, they're both the same. It's the same as when the two-dimensional Fourier transform is 0, because don't forget the Hankel transform is the two-dimensional Fourier transform for a special case. So anytime you do a Hankel transform, you think, it's a two-dimensional Fourier transform if that suits your ends. Okay, thank you, Justin. Perfect. Okay, I think what we'll do, we're running out of time. I'd like to save the next two until next time, and we'll start out the class with those. And I'm also going to give you until Thursday to look over your homework, to modify it, and to make it correct from what you've learned today, and then hand it in on Thursday. Is that okay? If you'd like to hand it in today, that'd be fine, but you have grace until Thursday. So yeah, we'll go ahead and do that. Any final questions or anything?
Dr. Marks?
Yeah.
I had just one thing. I realized today that I had forgot to submit homework 6 on the box, but I just did that before class. I don't know if that was fine.
Okay. How many want to excuse Justin? We'll do a democracy here, just like we're going to do on November 3rd. Okay, you can hand it in late, Justin. We have a majority. We have a majority vote. Okay, thank you, everybody. God bless and take care of yourselves. Bye-bye.
Thank you.
Bye.
Everyone.